So in this video, I'll discuss the relationship between hydronium and hydroxide concentrations. So recall when dealing with acids and bases, you have these two ions that represent the acid and the base. The hydronium is the H3O plus. You also sometimes just see H plus, the proton, but this represents an acid. And then we have hydroxide, which is a polyatomic ion, OH with the -1 charge, and that represents the base. So when we look at these two, there's a relationship between them. Recall that water can undergo autoionization, which means that it can automatically lose an ion. But water is a special molecule. This is known as an amphiprotic compound because it can lose or it can gain a proton. So in other words, water can act as an acid, but it can also act as a base. So essentially what happens is when water is present, you have both of these present, acid and a base. However, there's a relationship between them, which is based on that autoionization of water. So recall when dealing with equilibrium, equilibrium allows us to look at the rates of the forward and the reverse reaction. When they become equal, we can indicate how the equilibrium can be obtained. So how can we gain information about that system at equilibrium? And so in the case of the autoionization of water, we can have water acting as an acid, but we can also have it acting as a base. When it acts as an acid, it loses the proton. When it acts as a base, it gains the proton. So I can simply say that I have one water molecule that has gained, and I have one that has lost. So I have here, because there was a gain, the water to the left was my base. Here, the water to the right lost, so it was my acid. So the acid was converted to a conjugate base. The base was converted to a conjugate acid. So we have this acid and base thing going on throughout this system. And so when we were dealing with equilibrium constant, so that K or KEQ, we can look at it as products over reactants. So the concentration of products divided by the concentration of reactants. However, keep in mind that in the case of a heterogeneous equilibrium, or even in homogeneous equilibriums, there are certain physical states that are not included. Those physical states includes pure liquids as well as solids. So if we look back at this reaction, both of our reactants are liquids, so they would not be included. So what this means is that our equilibrium expression would simply be the concentration of hydronium times the concentration of hydroxide. That's equal to K. In this case, because we're talking about water specifically, you'll see it referred to as KW. And the W just means water. But it's still the same as K, KEQ. Ka will be calculated the same way if we were looking at how an acid dissociates. Kb will be calculated the same way if we were looking at how a base dissociates. So regardless of that subscript, it's telling us products over reactants if the products are in the aqueous or gas phases. So when we have water present, the equilibrium constant, or that autoionization constant, is equal to the concentration of hydronium times the concentration of hydroxide. Now that Kw value, again, is a constant. So at room temperature, which is roughly 25 degrees Celsius, that value is 1.0 times 10 to the negative 14. This is a constant value. It only changes when the temperature changes. So what this tells us is that if we know the concentration of one, either the acid or the base, we can figure out the concentration of the other, because the product of those two concentrations should equal 1.0 times 10 to the minus 14. And so this is a constant value. This is an equation that allows us to see the relationship between these concentrations. What that relationship shows us is that the products of their concentrations is always going to be equal to 1.0 times 10 to the negative 14 at room temperature. So for instance, if we were dealing with a solution that had, let's just say we had a concentration of hydroxide of 0.0136 molar. We can then use that information to figure out how much acid is present. Whichever one is present in a larger quantity tells us overall whether or not we're dealing with an acidic or a basic solution. If they're present in equal amounts, then we're dealing with a neutral solution. It is neither acidic nor basic. But in this case, we have our concentration of the base. So if I plug that into my equation, again, my Kw constant, 1 times 10 to the minus 14. That's going to be equal to, I don't know the concentration of hydroxide. I'm given the concentration of hydronium, I don't know the concentration of hydronium. I'm given the concentration of hydroxide. So I'm just plugging that into the equation. And this is just an example that I'm making up. So if you're given a problem, you may be given these concentrations. From there, you just put it in your calculator. I have to solve for hydronium. In order to solve for it, I have to get it by itself. Right now, it's multiplied by that hydroxide concentration. So I have to do the opposite, which is to divide. When I divide one side, I have to divide the opposite side. On the right side, they cancel out to simply leave me with hydronium. On the left side, I have to make sure I enter it in my calculator correctly. You have 1 times 10 to the negative 14 divided by 0.0136. And once you put that in your calculator, you end up with 7.35 times 10 to the negative 13. And that's your concentration of acid. So I can compare those two concentrations. In this case, because my concentration of acid is 7.35 times 10 to the minus 10 molar. My concentration of the base, the hydroxide, was 0.0136 molar. Because the concentration of my base is greater than the concentration of the hydronium, that lets me know that I have a basic solution. And so this is how you determine or identify the relationship between hydronium and hydroxide. Again, at room temperature, the product of those concentrations will always be 1 times 10 to the negative 14. As the temperature changes, that constant will also change, and you'll be provided with that information, but the constant will also change, but it's still the same thing. The product of their concentrations is going to equal whatever the value of that constant is. So in other words, as one increases, or if one is larger, the other is going to be smaller, or it will decrease. So I hope this helps. If you have any questions, please let me know.